On an island not so far away in the western part of the Baltic Sea, there's a project going on, a research project called EcoGrid. And Bornholm is about the size of Warszawa, has 40,000 people living there. And yeah, this is where we are talking about controlling heat pumps. So the Bornholm power system is, has some nice properties about it for research because it is isolated and not too big. It's connected by sea cable to Sweden, and we can so we can run in island mode when we need to do some experiments with the power system. And one of the properties of the power system is that it always has to be in balance. There always has to be a balance between production and consumption. And if there's a significant imbalance, that is going to result in either damages to electrical equipment or brownouts and blackouts. And in the good old days, production was very much controlled. We had central power plants producing power from fossil fuels. And because the grid is very much instrumented for live introspection, people can sit at the central power plants and control consumption or control production so that it always matches consumption. And since consumption is also quite easy to forecast, that makes it that made it sort of easy to figure out the balance problem earlier. But in the brave new world, where we're bringing in a lot of new power sources like solar energy and wind energy, which is not very controllable, we need some other tools for creating this balance. And in the EcoGrid EU, what we're trying to do is utilize flexible consumption as a manner of controlling consumption so that we don't have to control production as much. So this is about stuff like heat pumps and heat panels, electric cars, and washing machines, which, for example, with the heat, you don't really care when your heat panel is on, you just care about your comfort. So if you're feeling comfortable, you don't care about the rest of it. So what we're doing in EcoGrid EU is trying to control these heat pumps and heat panels. We have 1,000 pieces of those in Bornholm. And trying to push the time when they consume power so that it matches when we actually control power, when we actually produce power. And the system works like this. On your left hand, you have the TSOs and the DSOs, which are the grid operators who can forecast when they need flexibility from the consumers. And on the right side, you have the consumers who have installed some kind of smart heating equipment, home energy management system, stuff like that. And the consumers will sign up with an aggregator, and the aggregator then receives requests for flexibility from the grid operators. And then they have all those consumers who are subscribed to the aggregator. They can put all that flexibility into a big pool. And then they can bid into the market that we can offer 1 megawatt of flexibility, and then if they win, they can actually go out and activate the flexibility by turning off the heat or turning it on. Yeah, one more important part. EcoGrid 2.0 is a big research project running over 3 years with a lot of partners. Universities and very clever people who know a lot about the power system. We at Uptime, we are there to make things talk together. We are the ITC people who can hopefully figure out that problem. Because there's a problem with making all these kinds of things talking together. We have in our project just 2 kinds of different home energy management systems, but there are a lot out there already. There are going to come a lot of new stuff on board, and what we really want is for the consumers, if you buy equipment from Philips or Siemens or whatever you buy, you should not be locked into using them as aggregator, right? You have to be able to choose from any aggregator because they could offer you, some might offer you financial optimization of your consumption, others might offer you surveillance of your equipment and stuff like that. So it's kind of like your phone, you have to be able to switch carrier, so you have to be able to switch your aggregator, no matter what equipment you have. On the other hand, if an aggregator, if someone's thinking about becoming an aggregator, they want as big as possible a pool of flexibility in order to make money. So we have to solve the interoperability problem. And in EcoGrid, we talked a lot about, with the researchers who know stuff a lot about this area, how to design a protocol. And what we sort of came up with is, as our ideal version of the protocol is, we have, at the bottom, we have the DERs, which are the heat pumps, heat panels, distributed energy resource. And at the top, you have the aggregators, and the DER will phone in with the aggregator and establish a bidirectional communication channel, and then they can basically use a PubSub mechanism to talk to the aggregator. But in the EcoGrid project, as I told you, we have two kinds of equipment, and none of those can speak this protocol. So we have Siemens and Greenwave equipment, which sort of hangs onto their proprietary cloud solutions. And then we have the aggregators, and then what we're building in this project, and what I'm going to talk about today, is the flexibility interoperability platform, which offers a message broker for each of the aggregators, and then they have this virtual DER which talks to this new interoperability protocol, and then delegates into the cloud services in order to activate the equipment, or control the equipment. So why use Elixir for building something like this? We are not an Elixir shop yet. We have built some tools with Elixir, but the thing that really matters to us here is that Elixir has a great platform and has some great building blocks and the goals for the language. So the building blocks are how you structure your program, right? With data as structs, and then you have modules which you can with functions that describe your behavior. And I think this is common in most functional languages, but then Elixir has this processes thing, which is the secret sauce for a highly concurrent system. The goals of the language match very much what we want from a system like this. It has to be reliable, it has to be maintainable, and productivity is really important here, because we don't have unlimited amounts of resources to put into this project. But the platform is the most important thing. The fact that it has super solid runtime, can do lots of concurrency real fast. And then the share nothing memory model, and failing fast, and then controlling failures through supervisors is that really makes us, okay, we want to be on the beam, and the other two are the ones that make us choose Elixir. So what we want to share from this, what we learned building this system, is a few topics that we have learned something about, maybe got burned by. One of them is supervising dynamic processes, how to do collaborating processes which are isolated. Then some things about managing state and what goes wrong if you don't do it correctly. And then some other sort of learnings from production, like how to deploy, how to monitor a system. So supervising dynamic processes. At the top level of the application, we have it's built as one single application, like it's a monolith, like Sasha earlier talked about. We boot up, and then we boot up a metric exporter, which is a plug-in point for metrics. Then we have an Elixir registry that we use to facilitate communication between our processes. Then we have an Ecto repository for database stuff. And then we get to the application-specific parts, where we have a Siemens Supervisor and Siemens Manager, and GreenWave Supervisor and GreenWave Manager. And this is what it looks like for one of those trees, the Siemens virtual DER subtree. We have the supervisor and the manager. And then for each installation, each household that we need to connect to, we have a bunch of processes that need to collaborate. And these are all spawned by what we call an installation supervisor. So the top Siemens supervisor is a simple one-for-one or dynamic supervisor. So we can dynamically add and remove children. Then the next one is a one-for-one supervisor, which is with a permanent restart strategy. And it just spawns 5 children, a queue, a scheduler, a controller, an MQTT client, and an executor. And what the idea here is that when the system boots, the Siemens manager will go to the database, find out which installation it should start. Then it will send a signal to the Siemens supervisor to start each one. And then, since it's a simple one-for-one with a transient restart strategy, it should restart the children if they fail. But it should be allowed to be removed again, the children. Yeah. So that worked really well until one day we had a crash of an external system, which then impacted the amount of running processes. So you see, it's mostly just running about 2,000 processes until one day it drops to 500 processes. And we were sort of wondering what went wrong here, because it's supposed to be restarted if it fails, right? So we go to the log file, and we find this. The installation supervisor has exited with the reason of reached max restart intensity, meaning that one of its children has tried to restart one of its children too many times and has given up, and it's blowing up and then asking for the supervisor above it to handle this case. But actually, when the installation supervisor decides to give up, that's actually a normal error. So the transient restart strategy doesn't catch it. It says in the docs, if you read them, that if the supervisor reaches maximum restart intensity, then it will exit with a shutdown reason. And in this case, the supervisor will only be restarted if the supervisor above it has a permanent restart strategy. And so it's even more clearly in supervisor spec that if you're using the transient restart strategy, then it will only restart the process if it terminates with an exit reason other than normal or shutdown term. In this case, it's shutdown. So the process did not get restarted. So we were being a little too much naive about that, supervising dynamic processes. So I watched a talk by Fred Herbert just a few weeks ago from I think it was Elixir Days, and he explains like that's actually how it should be. You don't want your supervisor to be super complicated and trying to handle all these failures. Instead, you should have the manager there has to do some more work. So he has to continually be watching the children, if they are dead, if they are alive still. If they keep dying, try starting with an exponential back off, and then send an alert to someone so that their case can be handled. Because it would have gone even more wrong if we had used a permanent restart strategy, because then the installation supervisor would just fail too fast, and then this top-level supervisor would have died, and that would have crashed all the installations, so we would have lost data from all of them. So isolated but collaborating processes. These are the 5 processes in a Siemens installation, and they all need to collaborate, but they also isolated in that they don't really care that the controller doesn't really care that the queue is that queue that he talked to previously. It just has to be a queue that is handling messages for this installation. So they can come and go independently, just as long as they can always find one that they need to talk to. What happens when this system boots is that the MQTT client connects to the broker and the executor connects to the Siemens cloud. Yeah, I should maybe mention that the executor is there to actually execute commands against the Siemens installation. And the equipment out there is pretty fragile, we learned. You can't do any kind of parallel request against an installation. If you try to do that, you will just overwhelm it and it will go offline. So we have to manage carefully how much load we put on the equipment. So we put a queue in there, which is sort of a first in, first out, with a bit of priority scheduling in it. And then we have a scheduler which will start some jobs that have to run sort of every 10 minutes. We have to go out and scrape information from the device about what the settings are in the device. And then the controller there get messages from the MQTT client and converts that into commands to be sent by the executor. Yeah. So what happens when the executor is connected? It will start crawling the configuration of the Siemens device to figure out what it can do. And once it knows all of that, it will send a message to both the scheduler and the controller that it's now ready, and this is the configuration that they can use for generating commands. And then it will tell the queue to dequeue the next job. And right now the queue is empty, so it's just going to wait for a message to arrive. The scheduler then sends a start signal to itself, because now we can start scheduling jobs. It reads the configuration, generates a bunch of commands, and puts those in the queue. And then the executor will get the new commands, run it against the Siemens device, and then send the results back to the scheduler. And this is what happens when the messages come from the MQTT broker, gets to the client, it forwards it to the controller. It can then, depending on the message, it can maybe respond immediately, or it will have to generate a command that is in queued with the queue. Then the executor runs it and sends it back to the controller, which can then generate a response to the aggregator. And as I said, the queue knows a little about priority, so all the commands coming from the MQTT client are high priority, and the scheduler is low priority, and then it sort of, most of the time it will give out a high priority command. So yeah, what can go wrong here? It seems pretty simple, but when the system boots or the scheduler boots, it will just sit there and wait to get this message that the executor is ready. And the executor only generates this message once it is done booting and has crawled the configuration. So if the scheduler happens to crash for some reason, maybe talking to the database, and the database wasn't there, then it will crash, and the supervisor restarts and comes back up, and that's fine, but now it's just sitting there and waiting for the initial ready signal. And it's not going to do anything. So just because something is isolated does not really mean it's independent. You have to keep that in mind. One way this could have been solved is if the supervision strategy here was, instead of making it a one-for-one supervisor, it could have been a rest-for-one, and then if one killed it, one of them died, it would restart the rest of them. If the scheduler died, it would restart the executor, and then it would do all the stuff it had to do. But another way we solved it was just to make the executor check the config every 10 minutes so that it would at least get this ready signal after 10 minutes. So you just have to be aware of that. Making processes talk together when they are dynamic and going and coming away is actually really easy in Elixir if you use the registry. So this is how we did it. When one of these processes boots up, it generates an ID, which is used to register with the registry. And it does so giving it a value. In this case, it's a controller, which will then be used when someone needs to speak to the controller for this DR. We'll just ask the registry for the process like this. So in this case, it's the controller which needs to talk to the queue. So it just says registry find someone with my ID, and there has to be a queue, and then it can send the message to the queue. And then the registry also offers this dispatch function, which can be used for doing sort of pops up like things. In this case, this is the executor when it's done crawling the configuration. It tells the registry to dispatch for each entry that matches its topic. It will run through the list, and then if it's one of those processes that needs to know if that the configuration has been loaded, then it will send that message to the process. So the registry was added in 1.4 version of Elixir, and it works really well as long as it's on a single node, which we are in our case. So if you need to do something like that, just use it. I mean, alternatives are things like gproc or Phoenix pops up, or just normal naming the node by an atom. But I think the registry is pretty good because it has the functionality to do pops up like things when you need them. So expecting the unexpected. What's the schedule doing here? It sends a few commands to the queue, gets the results back from the executor, and then what is it doing? It's trying to save it to the database, the results, right? And we did it this way because we don't really care that much if the result is not stored. It's just something we're doing periodically to check if the customer out there has been changing settings on the device. And so we don't actually match on the return value. We just say, well, go and do it. And we're using the non-bang variant of the insert function because we don't care if it succeeds or not. But that's not enough, right? Sometimes it crashes anyway. And it turns out that if Ecto can't find a worker fast enough to do the actual insert, it will crash with a timeout of 5 seconds. At least that's the default, right? With the pool boy as your pooling library. So even though you think you're just trying to insert something and you don't care if it fails, doing this way is not safe because then you crash the scheduler. And that's why we had the other problem with the scheduler just sitting there and doing nothing. So yeah, don't just depend on a function being a non-bang. If you want to be really safe about the action you are carrying out, you should wrap it in a try-catch, or you should spawn a process to do it. So yeah, that was kind of a stupid mistake to make. And then we have these stateful processes, which are all mingling here with some other processes below the same supervisor. And looking at it, we knew that the MQTT client was prone to fail, and also the executor was prone to fail because they are talking to the external systems. So we keep those totally stateless, and we just make sure the state is the other 3 processes. And I thought I was super smart when I did that. But it turns out that, of course, if any of those processes crashes too quickly, and the supervisor gives up, then it's going to crash all the children. So there's a pattern that you should look into if you're doing stuff like that, the error kernel pattern. And so what we should have done in this case was to, instead of putting all those processes below the same supervisor, we should have some kind of nested supervision tree in order to ensure that the ones with important state don't get killed just because a supervisor gives up on restarting one of these volatile processes. And you probably cannot have too much supervision. So errors. This is just cut out from one of the module, a function that from the Siemens client that sends a request to the Siemens device, and it can get a lot of different errors back, like it wasn't a valid status code, or it couldn't decode the JSON, stuff like that. And what we did initially was just wrap all those up into tuples with an error as the first element of the tuple, and then the second element was something that described the error. And that works until a point, but then you get to when I need to log this error. Maybe someone is calling it, they need to put it in the log that they returned an error, or maybe you need to track a metric and you need to figure out, well, what kind of different errors do we even have that could be returned from this function. So instead of just returning error tuples with some kind of weird tuple describing the error, we decided to use the def exception macro to define a struct which implements behavior, and that is used by Elixir. So it just had to implement two functions, exception, which is a kind of constructor, and then message, which is used to return a string error that can be used to print the message in a log. So just very simple, we had one single module for all of our different error codes or errors, and then that kind of gives us one place to go and look for it, right? And now instead the code looks like this. So if you get an error back, we format the error. That's basically just calling error.exception with the tuple we want. Then we can just log it with error.message, and we can send it to a metric system for increasing the count of that kind of error. And that makes it easy to match on. You have just one place to go and look for what the different kind of errors are. And this was based on a blog post that describes the process by Mikhail, that just linked here. And yeah, basically, we put everything into one single error module because that was good enough for us. Of course, if you have a large system with a lot of different stuff, you should probably have a few of those error structs or error modules. So instrumentation and metrics. We use Prometheus to monitor the data center that is being used for this project. And not only can it capture metrics from all of our services, but we can also build it into our project. So we use the Prometheus EX library, which has all the things you need. And then when Prometheus goes to get metrics, it makes an HTTP request to your service, and it returns something that looks like this, a line for every kind of metric. And then it stores it in its database, and you can use it to make, or use Grafana to make dashboards that kind of shows how your service is doing. And we've been very happy with that. Maybe yeah, and comes standard. You can download this dashboard from Grafana. It has a lot of metrics from the Beam, like what is your process count, what is your load, what is your garbage collection looks like. And then you can make your own custom metrics, like you use Prometheus metric. You define a setup function which will be called when your application loads. And here you define the different kind of metrics you have. And then every time you have an error, you just call observe or some function that will increment the counter for you. And that's basically all you need. And we use this also to get metrics from Hackney, which is we use HTTP Poison for HTTP requests, and Hackney is kind of the one doing the work there. And it has an option where you can actually go and define which module you want to do error tracking with, and then you can define your own, and that's really nice. So yeah, do some monitoring. You can do Prometheus. There are tons of other options, but it just fit into our stack really well. And once you have a sense of what normal operations look like, you should set errors so that if you know your process count suddenly drops by 80%, you should probably send an error to someone. So deployment is all running on a single virtual machine, running Debian Jesse. And we use Ansible for all of the management, both of operating system and app configuration, and for doing deployments. And Ansible, if you don't know, is a kind of it's a system like for managing yeah, it's a configuration manager for your servers. And the tooling that we use is Distillery, which we use to build our release and then conform so that we can configure the release. Then we have built our own Ansible role, which does the job of building a release inside of a Docker image and then actually sending it to the server and just restart it to the service so that the new code is loaded. And then we use Vagrant for testing our deployments to make sure they work. And on the server, our release is being run by systemd. We tell systemd to forward its logs to our syslog, and then we use LogRotor to manage the logs. So this is super simple, doesn't require any kind of big expensive setup. Yeah, and it works well for us. The setup, when you need to get started with releases, you first install Distillery, you generate a release config, you add your conform plugin for managing configuration, and then you generate your configuration schema and a sample config file with conform. When we deploy, we use mix release, the command to build Distillery. We do this inside Docker to make sure it matches the operating system of the virtual machine we're deploying to. That produces a tar keyset file, which we SCP up to the server. And here we unarchive it to the proper directory and then make any changes we need to the configuration file. And then that sounds like a lot of work, but once we have it automated, it's just a single command to run it on production or staging or whatever environment you want to. So about configuration, just wanted to touch on that. Mix config is being baked into the sysconfig. Looks like that. Looks like this. It's not very nice to manage for people who don't know Elixir or Erlang. So we use conform to give us a sort of nice ini-style format of configuration. And this is done with conform you generate a schema file, as I said, which has information about all the different kinds you can configure through the mix config. And then it knows how to translate from the simple ini-style config to the sys.config. And the only sort of annoyance we've had with that is that the schema file has to be, every time you make a change to your mix config, you have to generate a new schema, and then if you have to sync it with the old schema, basically. But yeah, configuration is getting easier in the future, hopefully already in Elixir 1.7. But yeah, news releases, they've been baked into the system for the Erlang ecosystem for a long, long time. And they can give you what you need. We haven't used hot code reloading and stuff like that just because we wanted to keep it simple. I wanted to touch briefly on debugging. If you ship your release with runtime tools, then you have access to debug, and you just make a remote console into the machine. Then you type dbg dot, and you get all these nicely self-documenting functions for how to figure out what your system is doing, which doesn't work really well. But it worked for us in our case. When I was submitting the talk, we had the issue of why is nothing happening on this installation. We can see the schedule is there, why is it not doing things? We SSH into it, got the remote console running, set a trace for one of the processes, and then sudden, in the end we figured out that it was because it had been restarted and didn't receive the new signal to start getting data from the device. So I don't have a lot of experience with debugging in production other than that, but the tools are there. The platform is very introspectable, and you'll need some way to find your processes. We use the registry for this. And then don't use debug really if you want to. If you don't want to shoot yourself in the foot, get something like Recon or Tracer, which are more safe to run in production. As a kind of retrospective, things that worked well for us in this system. I talked a lot about stupid mistakes we made, but Elixir has actually worked really well. It has been running stable most of the time when we didn't do stupid stuff. We kept this application simple to ship it fast, and then using these exception structs, using Prometheus for monitoring, and using the registry turned out to be good decisions. Things we would have done differently: read the documentation more carefully, do more granular supervision, and more extensive testing of failure scenarios. Because Elixir is new to us, we should have spent more time working with docs and types, because it really helps when you're new to read the documentation. And then the last thing that we have started doing is to separate the concerns inside the gen server, because in the beginning we started out just having a monolithic gen server with the public API and the OTP callbacks and then the actual business logic inside one module. But then we heard about Dave's approach of separating these kinds of things so that you separate stuff, and that's a no-brainer. Just go and do it, I think. And that's it for me. Thank you for listening, and any questions?